In this video, I'm going to go through the time to climb questions that were presented in class on January 4th. This is for the high school physics course, and these questions are based on work, power, and efficiency. Okay, so let's go through the first one. How much work is done on a 100-kilogram crate that's lifted 2 meters in a time of 4 seconds? So here's my crate. It's going to be lifted up a total of 2 meters. And if you think about it, we're going to be doing a couple things. We could either think about this as work done is the change in energy. And in this case, lifting it up, I'm going to change its potential energy. So I could say work done is a change in energy. And in this case, that would be mgh. Another way I could think about it, it would be work done is the force times the distance. And remember this equation, force and distance have to be in the same direction. In this case, I'd be going against the force due to gravity, and the distance I'm moving is the height. Remember that the force of gravity is just mass times the acceleration due to gravity. And you see, we actually have the exact same formula. It doesn't matter which way we think about it. If I put this in here, mass of 100, I'm going to use G being 10 rather than 9.8 because I can see that all my numbers are rounded, times 2 meters for height, and I get the value of 2,000. The answer is D. Now, first, this looks like the same question. How much power is required to raise a 100-kilogram crate a vertical distance of 2 meters in a time of 4 seconds? But now I am looking for power. And if you remember power, it could be calculated as work per time or change in energy per time. So we can use the same kind of background that we did last time. My work or change in energy is mgh over the time. And if I put my values in, 100 times 10, raising 2 meters over 4 seconds, I'm going to get 500 watts. The answer is B. Okay, raising a car in a service station increases its potential energy, raising it twice as high, increasing its potential energy by, well, let's go back and look at the equation for potential energy. And we see here that the energy and the height are directly proportional. What that means is if I double the height, if I take this value and I times it by 2, and I keep these values the same, that's going to then double my potential energy. Our answer is going to be C. A model airplane moves 3 times as fast as another identical model plane. Compare the kinetic energy of the slower plane to the faster plane. So let's take a look at the equation for kinetic energy. Now, this is not the same because in this case, now my V is squared. So that means if my plane would move 3 times faster, that actually gets squared. We assume that our mass is going to be the same. That means my kinetic energy is actually going to increase by a factor of 9. So my choices are the same, no. Twice as much, no. 4 times as much, no. More than 4 times, yes. That will fit in with our value of 9. Which of the following equations is most useful for solving problems that ask for the distance a fast-moving box slides across the floor before coming to a stop? Now, first of all, we do know that that's probably going to be something to do with acceleration, so you might be tempted to say A. Our second equation there for B is our impulse formula. if there's a change in momentum. And yes, there will be a change in momentum because it had momentum and then it stopped. So if it, like, for example, ran into a wall or something. The third one for kinetic energy, it has kinetic energy and then it doesn't, which would imply perhaps saying um, all of our kinetic energy was used to overcome friction. And that's really what our last equation is here. F times d, that is work done. And 1/2 mv squared, that's the equation for kinetic energy. So what d is actually saying is the work done to overcome friction. So in this case, this F would be the force of friction, distance being how far we travel along the floor, is going to equal the change in kinetic energy. Now you might say it doesn't look like change in kinetic energy, but remember it finishes with 0 kinetic energy. Where did all that kinetic energy go? Well, it was transferred into heat when we overcome the work due to friction. So in this case, the answer would be D. A shiny sports car at the top of a vertical cliff has potential energy of 100 megajoules relative to the ground below. Unfortunately, something happens, it goes over the edge, and when it's halfway to the ground, then it wants to know how much about kinetic energy does it have. So let's assume that it just falls over the edge, and at the top, all it has is potential energy, and it has 0 kinetic energy. So now at the bottom, I know that's not what the question asks yet, but bear with me for a second. At the bottom, we're going to say it has no potential energy, and all of that potential energy has turned into kinetic. So if we take a little bit closer look at the equation for potential energy, mgh, what we're looking at right now is saying, okay, halfway down, that means my height is actually at 1/2 of the value, which means my potential energy at that point will be 1/2 of what it used to be. Haven't quite got to the answer yet, because if the potential energy is at 1/2, if we go back to this part over here, let's put in some numbers. If it started off with 100, that means there's 50 here. How much did it lose? 50. Where'd it go? Kinetic energy. So in fact, at this point here, we are going to have the exact same amount as potential and kinetic energy. In this case, 50 megajoules. Okay, which of the following is true about friction? Static friction is less than kinetic friction. No. If you think about that, it's always harder to get something going than it is once it's in motion. And some people might say, well, that's just inertia. Well, actually, there is a difference in friction as well. Friction only exists when an object is in motion. No. If you think about it, when you first try and push something and you don't get it going, that is static friction, friction involved when something's not moving. It's dynamic or kinetic friction once it is moving. So that's a definite no as well. Friction always opposes the motion or attempted motion? Absolutely. But let's just double check here. Friction acts in the opposite direction of the normal force. Well, if here's my box on the table, the normal force goes like this. And if I'm moving it, for example, to the right, then my friction would be along the surface here. They're perpendicular to each other, not in the opposite direction. So our answer really is C. A force of 250 newtons is used to keep a 65 kilogram crate sliding across the floor of a warehouse. What is the coefficient of sliding friction? Now, here's the thing. If it's sliding at a constant speed, That means that my applied force of 250 newtons is going to equal my force of friction. Why? Because if it's at a constant speed, we know that the forces are balanced. So horizontally, those are the only two that we have. So let me write that value down here first. 250 newtons. It's my applied force, but that's why it's going to also equal my frictional force. Now we have a mass here, so we do have force due to gravity, and we also have a normal force pushing up. Now, again, vertically, we don't have any acceleration. So, according to Newton's first law, those forces must be balanced. So, my normal force must equal my force due to gravity. I'm just going to use 10 here to make it simpler for my acceleration due to gravity. Remember, the force due to gravity is mass times acceleration due to gravity. Now, one last thing. Our equation for friction is mu Fn. So that coefficient of friction times the normal force. If I rearrange this, that says my coefficient is going to be my force of friction divided by my normal force. Now, when I put that in my calculator, I get 0.3846. And you might say, Mrs. Henderson, that should round down to 0.38. Well, remember that I did go and use 10 here rather than the 9.81 that I should have. That's why this value of 650 is a little bit bigger. And since it's on the bottom, it makes this value a little bit smaller than it should be. So my value is supposed to be here B, 3.39. A couple of things to point out. Remember, the coefficient of friction doesn't have any units because on the top and bottom I both had newtons and they cancel out. The other thing is that your coefficient of friction is typically a number less than 1. Not always, but I can't think of an example off the top of my head where it's actually greater than 1. When 100 joules are put into a device, we get out 40 joules. What is the efficiency? So I've put on here the equations that I gave in class. The useful amount out above the total amount put in, and it could be about work or power. Now, as I have it written there, it's going to give me actually just a decimal. In this case, I'm going to have 40 over 100. Realize, okay, 0.4, but if I want that as a percent, that is 40%. The answer is A. And finally, one of our favorite questions, yep, back to vectors. So we've got to create along 30 meters. And I do find that when I draw these diagrams as I'm talking, it actually helps me and solidify what's going on in the question. I'm pulling it at 185 newtons at an angle of 25 degrees. How much work does she do on the paper? Now remember, in order to use this equation, work is the force times distance. My force and distance have to be in the same direction. It's only going to be the component that, in this case, is the horizontal component along the distance of 30 meters that's going to contribute to the work done. So if I just look at this force vector here, it will be my hypotenuse that is going to be 185. There's the 25 degrees, and I'm interested in this component, not the perpendicular to the ground, but the parallel to the ground. And compared to my angle of 25, this is going to be my adjacent side. So I've got adjacent, I've got hypotenuse, I'm looking at cos. So I've just labeled that side X to make it easier. So I've got adjacent over hypotenuse. So how much is that? It's going to be 185 cos 25 degrees. Don't forget to make sure your calculator is in degrees. So if I just go back up here and I put it in all at one time, 185 cos 25 times 30, and I get 5,030 joules. Now, just a point to note out, if you don't have your calculator in degrees, you're not going to get that value. In fact, if you have it in radians, this particular one gives 5,500, and you might be lucky enough to choose the value close enough, but it is really important that you just double check that you are entering a value in degrees, and that's what your setting of the calculator is. Well, I hope this helps you out and helps remind you of some of the things that we've done with work, power, and efficiency.